Good afternoon. First, thanks, Wake, for giving us a wonderful presentation. It seems due to some system error, the topic is different. They upload wrong information. So anyway, good afternoon. This is Zhipeng Li from Washington State University, and my advisor is Dr. Xianming Shi. Today, I'd like to share our recent research using nanomaterials to modify a penetrating waterproofing sealer and protect concrete from soil scaling distress. This presentation consists of 5 parts. The first one, I'd like to introduce some motivation and background. The second one is the experimental program, and then followed with result discussion, conclusion, and our future plan. Soil scaling distress of concrete usually happened during the freeze-thaw and wet-dry cycles in the presence of some salt, especially the chloride-based salt like de-icer. So these two figures are classic soil scaling distress of concrete. The first figure shows a concrete pavement exposing to de-icer during the winter road maintenance. And the second picture shows the soil scaling distress of a concrete bridge pier in the cold marine environment. So how to avoid the soil scaling distress? The first principle is to keep the water and the chloride-based salt out. Surface treatment is a general used strategy to keep the water out and keep the salt out. So based on their function, surface treatment can be divided into three types. The first one is known as barrier coating. Coat a layer of sealer on the surface and then keep the water out. The second one is known as hydrophobic impregnation. That means use surface treatment to change the surface property of the concrete, make it hydrophobic. That means make the concrete hit the water and then keep the water out. The second one is known as pore blocker. So for some sealer, it will get into the concrete and then block the pores and the transport tunnels, and then the water is very hard to get into the concrete. So different surface treatment play different roles. So is there a surface treatment that can achieve all those functions together? The answer is yes. It's known as potassium methylsilicate, PMS sealer. So for this kind of sealer, it will react with carbon dioxide and then generate a very compact and hydrophobic film on the surface. It will also generate some hydration product like potassium carbonate and then block the pores and the tunnels to achieve a very good water resistance. However, so this sealer cannot work very well in a very aggressive environment. For example, like tire operation plus freeze-thaw and wet-dry cycles, and in presence of chloride salt. In fact, a lot of sealer cannot work very well in this scenario. So we want to enhance this sealer to make it stronger. So recent years, the nanotechnology in construction materials, its application is very hot. It's a very hot topic and again a lot of attentions. So as inspired by this technology and some previous nano-enhanced sealer research, so here we propose to use 2 foldable nanomaterials, graphene oxide and nanoclay, to enhance this PMS sealer. Here is the motivation and the hypothesis. So we assume the application of these two nanomaterials will modify the PMS sealers and improve its hydrophobicity by increasing its nano-micro hybrid roughness. And I will introduce more details later. The second hypothesis is that this PMS sealer is alkaline. So for the polynamic reactive nanoclay, we assume it will react with this alkaline PMS sealer and then generate more and more hydration products and then block pores. The third hypothesis is that graphene oxide is a fantastic nanomaterial. It can greatly improve the performance of cementitious materials. So here we assume it will catalyze the hydration process in the hypothesis 2. And this slide shows the basic information of these two nanomaterials that we used in this study. And we also investigated the chemical composition of this PMS sealer. It also contains some organic components. To guarantee the well dispersion of nanomaterials in this sealer, we use 30 minutes ultrasonic dispersion. So in this study, we use a two-stage experiment. The first one, we do some exploratory investigation and roughly determine the dosage of the two nanomaterials ranged from 0.050% to 0.15%. And once we determine this range, then we conduct a comprehensive experimental design. That means consider all possible dosage combination of these two nanomaterials. Here, the notation. Here is the notation 50N, 6G, and P means 0.50% graphene oxide plus 0.06 0.15% nanoclay plus 0.06 graphene oxide in this PMS sealer. And this is the best sealer that we obtained during our experiment. And I will introduce this a lot in later slides. So once we prepare our samples, then we start the water absorption test following ASTM, test the gas permeability coefficient. So in this study, we use the liquid micellar as the gas source. We heat this device to accelerate the evaporation of this micellar. Then we can calculate the gas permeability coefficient based on the mass change during this process. Then we also test the water contact angle and the penetration depth and the viscosity of these sealers. Finally, we run a accelerated surface scanning test. So based on the instruction from many commercial sealers, so in this study, the application rate of our sealer is fixed at 0.13 liter per meter square. Here is the water contact angle result. And the surface free energy can be calculated based on the water contact angles. So both these two parameters can be used to characterize the surface property. As we can see from these two figures, so after we adding nanomaterials into the sealer, the water contact angle increased. That means graphene oxide and nanoclay will increase the hydrophobicity of the surface. And this figures shows the possible mechanism of this enhancement. Figure A shows the two basic modes of the enhanced water contact angle enabled by this sealer. So after adding nanoclay and graphene oxide. These two nanomaterials will result in increased nano and micro hybrid roughness on the surface. We can learn from figure C. And during the hydration process, graphene oxide will also, serve as the growth template for some hydration products, and then generate some larger hydrates. It will also help to enhance this micro nano hybrid roughness. So this look like the lotus leaves. It's also a classic nano micro hybrid roughness. Then we test the water absorption behavior. So we can learn from these two figures that after we adding nanoclay and graphene oxide, the water absorption coefficient will decrease. So compared with the original mortar sample without any sealer, so this 50N6G and the P sealer decrease the coefficient by about 70%. So this decreased water absorption coefficient could not only be due to the denser microstructure on the surface enabled by these nanomaterials, it's also due to the increased hydrophobicity, as I discussed earlier. Gas permeability coefficient shows the similar trend with water absorption coefficient. Gas permeability is mainly depends on the internal transport tunnels. So this decreased gas permeability could be due to the block role played by nanoclay and graphene oxide, block the pores and then decrease gas permeability. And in addition, this decreased gas permeability also benefit to mitigate the rebar corrosion risk, because the oxygen, carbon dioxide, and the moisture vapor can not get into the concrete easily. So it helps to mitigate the rebar corrosion risk. Here is the sort scaling resistance. So as we can learn from these two figures, after adding these two nanomaterials, the mass loss during the freeze thaw process is decreased greatly. Here we test the surface roughness of the selected samples, and we find the introduced nanoclay also help to mitigate the surface scaling. So as I mentioned earlier, surface scaling distress happened when water come into the concrete with the salt. So the reduced water absorption and reduced gas permeability will help to enhance the salt scaling resistance. Nanomaterials looks very good, but however, we cannot add too much nanomaterials, because if we add too much nanomaterials, it will increase the viscosity of this sealer, and this is not very good, because with the viscosity increased, the penetration depth will decrease. So in other words, it's not a. So it may not very good for the practice. Based on the data, here we propose a relationship between the water absorption coefficient, water contact angles, and the gas permeability coefficient. So the result indicated that a decreased gas permeability and an increased water contact angle together will lead a lower water absorption coefficient, and then lead a better surface scaling resistance. here's the conclusion. So this study demonstrated the feasibility to use nanomaterials to enhance the engineering performance of this PMS sealer. So based on our study, this combination shows the best performance. Yeah, and we will continue the research using this combination. And this combination reduced the water absorption coefficient by 70% compared with the original water sample without any sealer. And it's also greatly decreased the salt scaling during the freeze thaw process. This sealer greatly enhance the hydrophobicity, and it will refine the pores, and then result a lower water absorption coefficient, and then results the better resistance to salt scaling. All those studies are focused on the new concrete. So our future work will move forward to some older concrete. So first one, we will do a field demonstration in Washington State University campus, and to apply this sealer to a pavement, and then evaluate its surface roughness and surface hardness. The second future work is we will conduct surviving analysis to this sealer. So the surviving analysis is originally developed to evaluate the effectiveness of new medicine on the patient. So in this study, we will treat this sealer as a medicine and treat the older concrete as our patient, and to see how it will affect the performance of our older concrete, and then obtain statistically reliable results. And this work was funded by National Treasury and thanks for donating the water reducer. And this technology was filed a long provisional patent. Any questions?
Yes, thank you. From the Swedish experience, we know that composites and other paintings, they do not work because they prevent the concrete from breathing, and then the moisture inside will cross damage. We know that traditional impregnation by using silane and silicate works very well, at least during 15 years. But your material does also seem to work well, but is it that much better than traditional impregnation? Is it cheaper, or have you made a comparison between silane and silicate and your material?
Yes. So we calculate the cost is cheaper, and the performance is also comparable to the traditional sealer. So it's a long time. I cannot the detail, but it seems the cost is less than $10. Yes. So and recently it seems the siloxane is very expensive because the limited supply.
The application of this is essentially on the surface, right? So does that, if you have traffic on the surface, does it come off? Do you have to reapply? How often would that have to be done?
Yes, so this is in our future work. So we will apply this in a pavement in our campus. So after that, I can tell you this answer.
Okay, got it. Thanks.
Actually, if I may clarify, this is a penetrating sealer. So like many of the other penetrating sealers, they have to go down, so they're not staying on the surface of the barrier coating, even though there's a little bit of film. So mostly it's going down.
Okay.
So most silane and siloxanes for bridge decks, they come out every 3 years. Usually you have to redo it because of the traffic operation. This one, we don't know for sure, but should be as good as cementitious. And another unintended benefit is this one is pretty low in those, volatile organic compound because it's water-based, so there's no solvent.
Yeah, I have two questions. The first one is, if you use a metal particles, is there any way to control the dispersion inside the concrete? They have some entanglement or extra one that spread and uniformly distributed particles. Do you have any idea how to achieve this kind of tool?
Can you say that again?
If you have a metal particle, you want to distribute evenly inside concrete mixture. So do you have any technique to achieve this goal, evenly distributed inside?
You mean disperse nanomaterials in concrete?
Right.
I think so far the ultrasonic dispersion is the best way so far, because it's very hard to evaluate the dispersion. Yes, but I can, so far we don't have some direct method to evaluate, but we can say the increase of strength, then we can know how well the disperse is. It's very easy. The strength increase greatly, then we may assume disperse is very well. But if the increase is not very well, then the disperse is may not very good.
The second question is I demonstrated reserve of freeze and tolling. And if we convert laboratory research into active practice, and we demonstrated 8 cycles, 8 cycles of freezing and thawing and the certain years of the site, you get an idea how to link between laboratory research and active practice inside. Maybe you can show your freezing and thawing results.
This one.
So I think next will be some pictures, nothing around previous, this one.
This one?
Yeah, it's 8 freezing and thawing.
So for this test, we prepare some concrete that the quality is not very good because we want it break very fast. So these 8 cycles, it's hard to say, but if we follow the real practice and prepare a very strong concrete, so it may much larger than 8 cycles. It's a.
Sorry if I may. This is a rapid freeze-thaw test in the presence of salt. So you're basically accelerating the filtration through several ways in the laboratory. So the water simulation is, don't remember, it's probably 0.45 or something. And was half entrainment, if I remember correctly. So it wasn't properly dosed in the entrainment. To try to make it deteriorate faster. And the sample is pretty small, so you get a lot of exposure to the isotope. And also the freezing rate of this test protocol is pretty fast. Like in the field, your structure won't go through the freezing cycle that quickly. So all these factors make it deteriorate much faster.
But that's the question, is how to read the literature is after the practice, so that instruments can develop.
Right. So the only thing is you can do a comparison. Let's say, hey, we improve the resistance to thaw scaling by 50% or by 60%. So but it's hard to translate. Say, hey, 8 cycles is equivalent to 8 years. Well, depending on where you are, actually, we'll have another thing to do about ACI. Depending on where you are, and if things are not accelerated to such a degree, you can get some rough correlation.
Any other questions? Right, thank you.
Thank you.